In today's video, we'll be talking about calculations with simple harmonic motion. Now, the way that I had this explained to me and how these equations are derived is, if you imagine here is our ping pong ball. Now, if I'm turning this in a complete circle like this, again, I'm just turning it in a circle on a horizontal plane. However, if I shift that circle upwards like this, and I'm turning it like this, eventually it gets to the point where the ball seems like it is oscillating. Now, if you don't quite understand what I mean, here are three drawings of the same circle, just from different views. So here is our bird's eye view, and our ball turns around this circle like this. Here is a tilted view, and the ball goes around the circle like this. And now here is a straight horizontal view. And so what may look like a straight line is actually our circle, just tilted even more. And the ball is still going around the circle like this, but from this view it just looks like it is oscillating back and forth through an equilibrium point. So that is why we use this example to get some of these equations. So this here is our first equation, and it says that our displacement from the equilibrium point is equal to the maximum amplitude times cos of the angular frequency, measured in radian seconds, times the time, just measured in seconds. Now, the reason that we get this is because when we're having a look at this graph, the maximum displacement is the amplitude, which is the radius, as that's the furthest away it can go at any point. And we know from SOHCAHTOA, C-A-H-T-O-A, when we're having a look at this one, cos is just the adjacent divided by the hypotenuse. So therefore, when we are looking for the adjacent side of an angle, it is just the cos times the hypotenuse, which in this case, the hypotenuse is r, as that's the radius. So it's r times cos of theta, where in this case, theta is our angular frequency times the time. Now, why is the theta angular frequency times the time? It's because if you remember back all the way to my circular motions video, the angular frequency, or in this case it was the angular speed, but it still applies, is equal to theta divided by time. So this equation is in your formula booklet, so you don't have to memorize it, you just have to remember how to apply it. But that's where it comes from. They haven't just pulled it out of nowhere. This is how they found it out. And this equation is, of course, for the displacement. So if you're ever asked to work out the displacement of something in simple harmonic motion, this is generally the equation that you want to come to. Now, let's have a look at our acceleration equations. So this is the first one that we have, and how do we get to this? So if you remember from my circular motions video, we went over the fact that acceleration is equal to omega squared times the radius. Now, we still use all of this stuff in simple harmonic motion, and because we are, as shown on the last page, again, putting in terms of circles, we can have a look, and the x component here becomes our radius, as from there to there, and we've worked out that x is just our cos of theta, because it's equal to the cos times the hypotenuse for the adjacent, which is the angle we're trying to find out there. So that means, therefore, we rewrite this as, instead of an r there, we end up with a is equal to omega squared times r cos theta. But because the displacement, as we've just seen, is equal to r cos of wt, this is practically the same as that, as our a is again just our r, and our omega t is just our theta. So we then write this as a is equal to omega squared x. And finally, to get this equation the same as that one, we have to put the minus sign there. Now, why is there a minus sign? It's because the acceleration is always acting towards the center of the circle. So that's our final first acceleration equation, where of course this is the acceleration, this is the angular frequency in radian seconds, and this is the displacement. So this is our second acceleration equation, and this is for the maximum acceleration when it'll be accelerating at its maximum. What is the value of maximum acceleration? And the way that we work this out is, if you remember to my last video, we learnt that the defining equation for simple harmonic motion was that the acceleration is directly proportional to the negative displacement, and the maximum acceleration occurs when it says maximum magnitude of displacement, i.e. when x is equal to plus minus a. So therefore the maximum acceleration will be the angular frequency times by the maximum displacement, which is just the amplitude. And here is a lovely little graph that shows how acceleration varies with displacement for an object moving in simple harmonic motion. So we can see here is our A max and here is our maximum amplitude or displacement. And finally we have our velocity equations, where this is the velocity in meters per second. Of course, this is our angular frequency in radian seconds. This is our amplitude or our maximum displacement, and this is just our displacement. Now, you don't have to worry about the exact derivation for this, but it's basically just, if you think back to old trigonometry, c squared minus b squared is equal to a squared. Almost forgot to mention, this plus minus here comes from the fact that velocity is a vector, so it can either be going in a positive direction or a negative direction. And our final equation is that the maximum speed, which is Vmax, is equal to the angular frequency in radian seconds times by the amplitude. Now, a final useful thing to note is that, of course, the angular frequency, when we were talking about angular speed, we said that it is equal to 2 pi f, or the same still applies. So you could quite easily rewrite this equation as Vmax is equal to 2 pi f a. And again, because in physics we love our graphs, here is one for how the velocity varies with displacement for an object moving in simple harmonic motion. Now don't worry, it's not meant to be a circle, I'm not that awful at drawing. It's meant to be an oval, however it's not a very well done one, but you can sort of see what I mean. So let's move on to some questions. We have been told that a mass is attached to a horizontal spring and it is pulled 7.5 centimeters from its equilibrium position, and one complete cycle it takes 1.2 seconds so for it to go up and back. We have been asked to find the frequency of the oscillation of the mass. We've been asked what the magnitude of its maximum acceleration is and what its speed is when it's 2 centimeters from its equilibrium position. So let's start off with the first one. What is its frequency? Well, we know that f is equal to 1 divided by t, so therefore 1 divided by 1.2 is going to be equal to our answer, which is 5/6, but we never write in fractions, so it is equal to 0.83, giving it to 2 decimal places because that is the maximum amount of decimal places we have been given. Next, let's find the magnitude of its maximum acceleration. So we know that A max is equal to omega squared A. However, we've got the maximum amplitude, which is 7.5 centimeters, which we will convert to 0.075 meters, as we want to use meters and seconds, not things like hours and centimeters. So we want to find out what is the angular frequency. Well, luckily we have the normal frequency, and we know that angular frequency is equal to 2 times pi times a normal frequency. So therefore, we end up with this, which comes out as 5/3 pi, or 5.235. No. And if we were just being asked to find out the angular frequency, you'd leave it like this in 2 significant figures. However, I'm going to continue using this number as it is more accurate for the rest of our equations. Now that we know our value for the angular frequency, we can put it into this equation. So we know that A max is going to be equal to 5/3 pi squared times by 0.075, which comes out as this lovely number, 2.05, but we put it as 2.1. And then what's the acceleration? So that's going to be meters per second squared. Put it as 2.1, not 2.05, because it rounds up and we give it to 2 significant figures, as that's what everything we have been given is 2. Finally, let's work out its speed at 2 centimeters away from its equilibrium position. So we know that v, which is our velocity or our speed, is equal to omega times the square root of the amplitude squared minus the displacement squared. Now obviously we put plus and minus here, but because it's not asking us for more than one direction, it's just asking us for 2 centimeters out what speed it is going at. We are just going to consider it in the positive direction, as there is no need to involve the negative. So we've got all our numbers. All we have to do is convert 2 centimeters into 2 meters. So therefore we end up with our velocity being equal to 5/3 pi. Again, you could use the number that came out on the calculator for this. However, this is far more accurate. Times by the square root of 0.075 squared minus 0.02 squared. And this gives us this lovely number, which we will give to 2 significant figures, as that is the highest amount of significant figures we have been given. So therefore the velocity at 2 centimeters from the equilibrium position is equal to 0.38 meters per second. That's all for today's video. Thank you for watching. Again, I'm not a physics teacher, I haven't even sat the A level yet, so if I got anything wrong or missed anything out, please let me know in the comments. I hope I could help. Bye bye.